So this is day 2 of section 2A, derivatives as a function. Let's remind ourselves, this isn't a ramble, this is a reminder. Let's remind ourselves what we learned on Friday. We're talking about the derivatives as equations. We talked about a derivative being equal to the slope, right? The derivative of a function is equal to the slope of a line at any given point, right? The slope of the line at any given point. But if we can somehow create an equation so that my input value was the x value, but the output value was the slope, that's what we're talking about here. The derivative as a function, okay? And that's kind of what we started out by doing here. Remember, we did this whole process where we said, okay, where's my pencil line? Like, is my slope increasing? Is my slope decreasing? Is my slope positive? Is my slope negative? And then we use that same input value and then the output value being the slope to create my new graph of my derivative, okay? We'll do this a lot later, a lot. We will do that in great depth. And then we did a couple examples where we just like worked with it algebraically. Said, okay, if this is our formula, x plus h minus f of x over h, algebraically solve and reduce it down and see what our function would be as h goes to 0. We did that with a polynomial. We did it with a square root. Remember, whenever you have the square root, remember you got to do that whole thing where you multiply by its conjugate, numerator to denominator, just to see what would happen. Maybe hopefully things would cancel. And then we did this thing where I recorded you guys saying, remember, this was you're going to appreciate the shortcuts when we learn them later on. All right. So that was more on the algebraic side of it, right? That was more on the algebraic side of it. This whole section is more on the algebraic side of it. Let's talk about some other different types of notations that you may see. Okay. If we use the traditional notation y is equal to f of x to indicate that the independent variable is x and the dependent variable is y, then some common alternative notations. Now, these are not all used widely. Most of the time you're going to see that y prime or f prime of x, right? This is the one that's used most often by me, at least. I don't know. Maybe other people might use some more often, but again, it's just their preference. This one I have seen a lot of as well, though. dy dx. I know that's more of like the AP class uses that a lot. That's just another, if you ever see dy or dx, dy over dx, that is just saying, okay, that's the derivative of the function y, of the relation y of x, okay? It's the derivative in respect to x. And we will actually talk about it in the derivative with respect to other variables as well, okay? If there's multiple variables going on and we want to, find the derivative, we can do that. Okay. This one is not used very often, df dx, because if you're going to call it a function f, it's more often used f prime. But still, this, if you're going to use this type of notation, that's usually what we see. D over dx of f of x. Okay. Sometimes it's capital D. I don't really see these much very often. Mainly, it's f prime, dy dx, or d over dx of f of x. These two are very similar. The only difference between those two is that one of them is just for any relation y, and one of them just is using f of x. Okay. The symbols d, the capital D and the d over dx are called differentiation operators because they indicate the operation of differentiation. They're saying, okay, when I apply the operation of differentiation, because really, it's an operation now. We're doing it to a function to create a new function, so it is an operation. When we do the operation of differentiation, when we find the derivative of the function, that's what we're really doing here. We're saying, okay, I'm taking d over dx of f of x. That's just a notation saying, find the derivative of f of x. Find the derivative of y. Okay. This was first introduced by this guy named Leibniz. He's kind of like the head honcho of calculus. Like he's one of the guys that like created calculus. I think his first name is like Alfred or something like that. Alfred Leibniz. He was the first guy to really use the dy over dx notation. Now it's not a ratio. Don't think of it as like a quotient or anything like that. It's simply just a synonym for f prime of x. Okay. Now let's talk about when a function is called when a function is called differentiable. Differentiable. Okay, differentiable. You're going to hear that term a lot. A function is considered differentiable at a certain place if the derivative at that place exists. That's pretty simple. That's pretty self-explanatory there. You can call it differentiable if the derivative exists at that place. Now, it is differentiable on an open interval a to b, or the other type of notations here, if it is differentiable at every number within that interval. Now, we're going to talk about when are things differentiable. When can we find the derivative at these places? Okay. Oh, I went down way too far. So let's talk about this. Where is the absolute value of x differentiable? Where is the absolute value of x differentiable? Now, I think you guys would agree that the absolute value of x is really kind of like two different functions going on, right? We talked about it as piecewise early on in this course. So let's do the same thing. Let's say, okay, if x ends up being positive, and then we're going to explore it a little bit, and then later on we're going to say, okay, if x is negative, something else may happen. So let's explore the possibilities of it being positive. Okay, if x is positive, what is the absolute value of x really equal to? Just x, right? Okay, if that's the case, then this is going to be true. If f prime of x is really going to be equal to, remember it's the limit as h goes to 0 of, I'm going to write it up here. Limit as h goes to 0 of f of x plus h minus f of x all over h, right? That's our definition of a derivative. So I'm going to say the limit as h goes to 0 of the absolute value of x plus h minus the absolute value of x all over h. Okay, if x is positive, then x plus h is even more positive, right? So it has no possibility of going into the negative direction. So x plus h, I can take off the absolute value there, minus x, because the absolute value of x is x, all over h. Well, what happens to my x's now? So long, farewell. So it's h over h, which is just 1, right? So I can say the derivative is equal to f prime of x is equal to the limit as h goes to 0 of 1, which is the limit of a constant is the constant, 1. Think about it in terms of the other side of the graph. If the absolute value of x is less than 0. If the absolute value of x is less than 0. Well, if the absolute value of x is less than 0, then the absolute value of x is really equal to negative x, right? The opposite of x. If x is negative, then the absolute value of x is equal to negative x. See, if it was negative 2, I'd need to make that negative cancel out by just taking a negative in front of it. Negative 2 turn positive 2. Well, if that's the case, then now f prime is going to turn to this. It's the limit as h goes to 0 of, okay, it's still the same thing, x plus h minus absolute value of x all over h. Okay, so now this turns into negative, this whole thing, minus negative x. It's net negative of that whole thing, all over h. Okay, distributing that negative sign. That's going to be negative x minus h plus x all over h. And look at that, fancy dancy, that cancels out again. Negative h over h turns into negative 1. So, the limit as h goes to 0 of negative 1 is negative 1. Now, I shouldn't have needed to show all of that. Here's why. Think about the function that we were using. Think about the absolute value function. What's the slope on the right side of this graph? Positive 1. What's the slope on the left side of this graph? Negative 1. So it makes sense that if x is positive, it's 1. If x is negative, it's negative 1. Now here's the weird piece. What piece have we not thought about yet? 0. We haven't thought about 0 yet. We haven't thought of it because we did if x is greater than 0, if x is less than 0. Okay, if x equals 0, okay, if x equals 0, then what's going to happen? Well, this is going to be the limit as h goes to 0 of this whole x plus h, minus absolute value of x all over h. Right? If x equals 0, well, then we know this. This is going to be the limit as h goes to 0 of 0 plus h minus absolute 0, which is, okay, well, 0 plus h is the absolute value of h over h. And what we want to do is find the limit as h goes to 0. Well, can I do, we want this, right? Can I directly substitute there? Can I just call it 1? Can I just call it negative 1? Not really. So here's what I have to do to examine the limit, which is actually something that we already did in a previous lesson. We have to examine the limit from the left and then the limit from the right. The limit as h goes to 0 from the left, and then the limit as h goes to 0 from the right. Okay, if it's from the left, then it's that negative 1, right? Oh, sorry. Yep, it's that negative 1. It would be negative h over h, which is negative 1. If it's from the right, that would be positive h over h, which is positive 1. So let me ask you, does the limit as h goes to 0 at 0 exist? No. The limit does not exist here. At this location right here, the limit does not exist. So what does that mean? That means that at that point, this is not differentiable. It is impossible to find the derivative at that corner point, at that point where it comes to a nice, clean edge. I am not saying that, think about this. Was that point rounded out at the bottom? No, it came to a nice, clean point. So as soon as I flip over, actually, you know what? Let me not draw the axis in there. If I think about the actual absolute value function, and I'm thinking about the slopes, as soon as I flip from one to the next, as soon as I go down, okay, I'm getting to this point, does it ever like curve out at the bottom? No, it just flips, right? The slope is never 0. It flips from one to the next without hesitation. As soon as it gets to that middle point, it flips to the other side, which means that it's not differentiable, okay? If f is differentiable in A, then f is continuous at A. So we actually have two different things. And the first thing that we saw when it was not differentiable was this corner point, like on an absolute value. But now this theorem is saying that if f is differentiable in A, then f is continuous at A. Oh, so that whole time we spent studying discontinuities, that's why it's important. Because if you have a discontinuity, guess what? It's not differentiable at that location. So if you see a jump, you see an infinite discontinuity, you see a removable discontinuity, you know that the derivative does not exist at that location. It is not differentiable at that location. The derivative does not exist. Okay? Now, this is not, the converse of this is not true. The converse of this is not true. If you say it's continuous, that doesn't necessarily mean that it is differentiable at all those locations. We saw it in the last example. We had the absolute value, but was it differentiable at that corner point? No. Is that a continuous function? Yes. So the converse of that theorem is not true. Just because it's continuous does not mean that it's differentiable anywhere. So what are the limitations on differentiability? What are the limitations on when it's differentiable or not? Well, we talked about the corner point. The funny thing, they call it a kink in the graph, which I think is really weird. Like, why use that term? I don't know. I know. But I call it a corner point. A corner point, where it comes to a nice, clean corner. Okay, you call it whatever you want. So if the graph ever has a corner point, then it's not differentiable. Now, I'm not saying a rounded out point. It is differentiable at all those points if it's rounded out, like it's a parabola or something like that. A corner is different. A corner is different. A corner is different. It's going to flip from one slope to the next without any piece in between. Okay. Another one is when we have a vertical tangent. Okay. When you have a vertical tangent. When you have a vertical tangent, it is not differentiable. Think about why. Think about why. If I had some sort of function and I was graphing it along and then it went like that. You know, the slope is the derivative, right? The slope of the tangent line is the derivative. Let me take my pencil and trace along. Okay, what's the slope as I go right here? What's the slope of that line? What's the slope of any vertical line? It's undefined. So because the slope of the vertical line is undefined, as soon as my pencil goes straight up and down, it's not differentiable at that spot. Okay? If you ever have what's called a vertical tangent, if it ever goes on top of itself at any point, if it ever bends through, it is not differentiable at that spot. That's what's called having a vertical tangent. So really, I'm showing you the 3 times when you cannot find the derivative of a function. The 3 instances. You guys are so loud. Can you be quiet, please? I really wanted to just go into that whole crowd and start yelling. Yeah. Okay, back to calculus. So the 3 times when something would be not differentiable, okay, the 3 times would be a corner point, a discontinuity, or a vertical tangent. Okay, a corner point, a discontinuity, or a vertical tangent. Is this the only type of discontinuity? No. Jump discontinuity, that is a jump discontinuity. A removable discontinuity or an infinite discontinuity. Those are the 3 types of discontinuity. Okay? So, corner points, vertical tangents, or any discontinuity, that means that the derivative does not exist at that point. Okay? Something else must happen. Okay? All right. Now, just like you can take a single derivative, you can take a double derivative. What happens if you find the derivative of a derivative? What happens if you find the derivative of a derivative of a derivative? What happens if, and that process could keep going on. Now, there are different implications. There are different implications if you keep going. Okay? There are different things that may happen. But it is possible. If f is a differentiable function, then f prime is also a function. So that must mean that if we find the derivative at f prime, we can find f, what's called f double prime, or f triple prime, or f with, and then you keep just adding slashes. You keep just adding apostrophes up there. Okay? How does that look like in the other type of notation? You would just write it like this, like the dy over dx notation, d squared y over dx squared. Okay? It's the second derivative of that function of y as it pertains to x. All right, now, we have already found the derivative. We have already found the first derivative. We have already found the first derivative. So if you wanted to flip back, you could, but, you know, I know because my rules of derivatives, it's just that. 3x squared minus 1. So that's f single prime. It says, okay, now find f double prime. F double prime. Well, f double prime would then be, well, the limit as h goes to 0 of f of x plus h minus f of x all over h. So 3x plus h squared minus 1 minus 3x squared minus 1 all divided by h. F of x plus h minus f of x all over h. And now we reduce, because again, we can't do direct substitution. Make sure I'm on the right track here. Yeah. All right. So we have 3, and then this FOILed out is x squared plus 2xh plus h squared minus 1. Let's bring in this negative, minus 3x squared plus 1 all over h. So we have 3x squared plus 6xh plus 3h squared, just distributing in the 3, minus 1, minus 3x squared plus 1, all over h. Okay, let's start canceling. So long, goodbye. Oh, that's it? Oh, no. Those ones go in. Okay, so this is a 6xh plus 3h squared all over h. What do I do with my h's? They go bye-bye. This one goes bye-bye, that exponent goes bye-bye. So we have 6x plus 3. Now, remember, 3h, excuse me. 6x plus 3h. Now, remember that this is the limit as h goes to 0 of this thing. So that means if h goes to 0, what happens to my 3h? 6x. So f double prime of x is 6x. Now, it should be decreasing in complexity, especially if it's polynomial. It should look like it's getting simpler each time you go to find the derivative. Each time you go to find the derivative, it should be getting simpler and simpler and simpler. Now, what does that interpret to be? What are the interpretations of double derivatives or triple derivatives and so on? In general, we can interpret a second derivative as a rate of change of a rate of change. You know, a derivative itself is a rate of change. So basically, you're looking at how quickly is the slope changing. Okay, that's what you're looking at with the double derivative. How quickly is the slope changing? So think about a quadratic as it compares to an exponential. Do you know how a quadratic, it goes up pretty quickly, but doesn't an exponential go up quicker? The rate of change is faster in an exponential rather than a quadratic. So the double derivative of an exponential would get you a bigger number than the double derivative of a quadratic. Okay? Mathematically, that's how we can apply that. Now, what about like this whole physics thing where I say the derivative of position is velocity, right? If I take the derivative of a position function, you get velocity. So what's the double derivative of position? Well, think about the derivative of velocity. What's the rate of change of velocity? How fast does velocity change? That's acceleration, right? Isn't that acceleration? So how fast does velocity change? Acceleration. So that must mean the double derivative of position is acceleration. Acceleration is truly the double derivative of position. Now, what is third derivative? What are the implications of that? Well, then there becomes less and less real world implications once you get into double, triple, quadruple derivatives. Like you get into deep. It's like the rate of change of the rate of change of the rate of change. Right? Then it's like, whoa, I don't know, shut up. Yeah. Okay. We do talk about. Well, we don't really discuss this too often, but think about the rate of change of acceleration. Okay, the rate of change of acceleration, because that's the double derivative of position. The rate of change of acceleration, the derivative of acceleration is called jerk. Okay, it's called jerk. It's not something. It's not like what you call the people next to you. If you may have them. It's like how quickly does acceleration change? Okay, that's jerk. Jerk is the triple derivative of position. Okay, it's how quickly your rate of change is increasing. Okay? So let's do this one more time. This is our last example here. We're going to find the third and fourth derivative of this function that we were looking at. Now, I said to you it was supposed to get simpler and simpler and simpler. What was the double derivative? Well, you know what's fun here? Okay, so the single derivative would have been this. The double derivative of this is this. Let's look at triple derivative. Let's look at triple derivative. This is f prime. And this is f double prime. Now, let me ask you this. Because I bet some of you can figure this out. Is there a pattern that you see? You say it goes up by 3 each time? Well, this was 1. So it went up by 2, then 3. So that's not good. What did you say, Kelsey? Take the exponent. Stick it on the front. And then what did you do with the exponent? Does that work again? Take the exponent, put it down front. 2 times 3 is. And then what did we do with the exponent? Drop it down 1. So what happened with this guy? What was the exponent? 1. Drop it down 1. What is x to the 0 power? Okay, what is the variable here? X to the 0, right? Was it x to the 0? Well, 0 brought around front. 0 times 1 is nothing. I wonder what the third derivative is then. Anybody have any guesses what the third derivative is? You say 1? What's the exponent here? So you'd bring it out front and multiply, right? And then it would be 6x to the 0, right? And what is x to the 0? 1. So we think it's 6? Let's see. Okay, we're taking this. We've got the limit of x plus h minus f of x all over h, right? F of x plus h minus f of x all over h. All right, let's distribute in. 6x plus 6h minus, 6x plus 6h minus 6x. Cancel, cancel. This is still all over h. 6h over h. What happens? So what is the limit as h goes to 0 of 6? Oh, we were right. Now, what do you think this is? Because this would have been this, right? Right? 0 brought around front. What's 0 times 6? Let's see if that's truly the case. Let's see. So now we're finding the fourth derivative. So this is this, right? This was not there. Okay, it's f of x plus h, right? Is there anything to plug x plus h into? So the function is just 6, right? We should say the limit as h goes to 0. F of x plus h minus f of x all over h. What's 6 minus 6? What's 0 divided by anything? Okay, so it's the limit as h goes to 0 of 0, which is 0. Ooh. See, this is all chapter 3, figuring out what are these patterns and seeing if you can see a pattern there. All right, that's all we got for today. That's interesting. We're seeing this pattern already. That's kind of cool. All right, let me turn off the video.